So the next reaction we're going to talk about in terms of electrophilic addition is the addition of halogens. So remember X means just some halogen. So X2 is the versions of natural versions of halogens, so like Br2 or Cl2. Halogens react quite well with double bonds, and they still do the basic electrophilic addition where we break the double bond, we form two single bonds, and what goes on those two single bonds are two of our halogens. So whatever halogen we're starting with, each carbon that was in my double bond is going to get one of those halogens. So in here, things are going to be a little bit different in terms of the mechanism, and that's okay. And also here, we don't really have Markovnikov's rule because our electrophile and our nucleophile are the same thing. So each carbon that was inside of my double bond is going to get a halogen. So there really is no need to look at the more and less substituted side. So with the mechanism now, we are going to see, once again, we're starting to learn more and more about organic chemistry, that sometimes in certain mechanisms there might be a named intermediate. So the intermediate that we form is got a formal name, and you're expected to know that name. So the intermediate that we form after the first step in the mechanism of bromination is called the bromonium ion. So once again, I wouldn't particularly have you draw that out, but you need to remember that after the first step, this three molecule intermediate is called the bromonium ion here. And so we're going to find that out. Sometimes we have named intermediates, and you need to know the name of that. So when we look at the mechanism of the addition of Br2 or any one of our halogens that we're adding to a double bond, it's kind of a little bit different. It's still a type of electrophilic addition. You remember our bromines, Br2, they have 3 sets of lone pair electrons. I like to call this kind of the two-way street here, where the lone pair electrons on one bromine attacks a carbon. So lone pair electrons attacking an atom forms a bond. So this is where this first bond between bromine and carbon comes from this first arrow. The double bond or the pi bond inside of here, the electrons in the pi bond also attack the bromine. So a bond attacking an atom forms a bond. So the electrons attack the bromine, that forms this second carbon-bromine bond. And in the last step, or the last part of this mechanism, we break the bromine-bromine bond. These electrons jump on to this bromine. This is going to form Br minus, and we're going to see this again in just a second. But overall, what we've done is we've broken this bromine bond, and then we've gotten rid of our pi bond here, and then we've formed two bonds between our bromine and our carbons here. So we end up forming this 3 molecule intermediate called the bromonium ion. So onium means positively charged, so that's why it's called that. The bromine has a positive charge in this case. And this now is very viable to attack. So this 3-membered ring really wants to be broken. And remember, from here we popped out a bromine, Br minus. Remember, halogens are a good nucleophile, and so we're going to get a type of SN2 attack in the second step. So the bromine that we created, so this bromine right here came from the bromines breaking apart, can come in and attack this 3-membered ring, and it's actually a type of SN2 nucleophilic attack. So this bromine makes a good leaving group, this bromine comes in and attacks. And you can see this leaves a very distinctive kind of positioning between the bromines. We're going to talk about that in just a second. But remember, this comes from backside attacks because it's an SN2 reaction. This bromine is going to attack from underneath, and it's going to push the bromine on top. So these two bromines are going to be positioned on opposite sides of our molecule here. And so we call this positioning anti. And this is one of the other things that we're going to get, that beyond Markovnikov's rule, when we do electrophilic additions, we can be very defined in terms of the positioning of the two species that we've added. Remember, overall, you break the double bond, if you form two single bonds, what goes on those single bonds. You also need to be aware in certain occasions that the positioning of these two bonds that we make are going to be very specific. And so with the bromination of a double bond, the two created single bonds are on opposite sides of the molecule. And I'll show you here that there's a better way of looking at this. But this positioning where the two formed bonds are on opposite sides, so in this case one's going up, one's going down, this is called anti-positioning. And so this is one of the things you need to remember when you're looking at a product. You need to take a second and say, okay, do we obey Markovnikov's rule? And then the other one is there a defined positioning of the two bonds? And so with the bromination, we get an anti-positioning. So how I like to look at it is by using a ring. So when we talked about rings, there's a defined upper and lower part of the ring, and that makes it very easy to see this anti-positioning that we're talking about here. So here I have cyclopentene. I've added Cl2 to it, our halogens. We're still going through the same basic process. I break the double bonds, I form two single bonds. What goes on those single bonds is a chlorine on each one. So I form two single bonds, one a chlorine, the other one's a chlorine. But I need to be very specific. I need to show that one chlorine's on one side, the other chlorine's on the other side. So I've used dash wedge positioning here. And there's a few different ways you can show it, but with the bromination or halogenation of a double bond, you need to be very clear to show that the halogens are on opposite sides of the species here. So one chlorine's going up, the other one's going down. And this is a ramification of the mechanism, the formation of the three-membered ring. So in this case, we would form a chloronium ion, and then we get a subsequent SN2 attack. That's what causes these two halogens, the chlorines, to be on opposite sides. And so we want to show that. So there's a defined upper and lower side of this ring. I show that the chlorine and this hydrogen are on one side by using the wedges. This hydrogen and this chlorine are on the opposite sides by showing them as dashes. So overall, we've broken the double bond, we formed two single bonds. What goes on those single bonds? Okay, two chlorines. But beyond this, I need to be very clear in showing that chlorine is on one side and the chlorine's on the other. So this is always true. So here we look at another example of it. Remember that we're going to be talking about a few reactions that involve a double bond. That reagent tells me what reaction's going on. So I say I start with a double bond, I react it with bromine, and then that's going to be the question is what's my product here? The bromine tells me I'm doing a bromination. So I say, what do I have to do to my reactant to make a product? In this case, I break the double bond, I form two single bonds. What goes on those single bonds? Okay, a bromine on each piece, but I also need to make sure to show that the two corresponding halogens are on opposite sides of the molecule. So one bromine is going up, the other bromine is going down. So just to keep track of things, this carbon is this carbon is this carbon. So I've broken the double bond, formed two single bonds, I've put a bromine on each one of them, and then I've made sure to show that there's a bromine going up and a bromine going down. So the next reaction, this one also has a name, it's called hydroboration. And with this, there's a slight difference, and we will go over this. Why are we so concerned with putting, an OH on one side or the other? We will get to that. But we've already seen with the hydration, when I add water and H2SO4 to a double bond, we end up adding an OH following Markovnikov's rule. Well, what happens if I want to add an OH to the other carbon? And in this case, we mean anti-Markovnikov, or the nucleophile or the species that we're interested in goes on the less substituted carbon. In order to do that, I need to change my reaction, and this is where hydroboration comes in. So overall, when we look at this, we're going to be adding our OH anti-Markovnikov, which means to the less substituted carbon. So overall, the same basic steps are the same. During hydroboration, I break the double bond, I form two single bonds. What goes on those single bonds is a hydrogen and an OH. So just like what we did with hydration, but the difference now is we go anti-Markovnikov. So I go back to my reactant, I say, is there a more and less substituted side? Okay, yeah, this carbon has two substituents. This carbon has one. This is my more substituted carbon. This is my less substituted carbon. So the less substituted carbon gets the OH in this case. So I break the double bond, form two single bonds. What goes on there? An H and an OH, and the OH goes on the less substituted carbon. That's what we mean by anti-Markovnikov. So with this reaction, it's broken into two steps. And so we saw with the Williamson ether synthesis that we had two steps where there was kind of two reactions that we put into one. And that's what we mean when we use this nomenclature of 1 and 2. It means that there's two kind of reactions going on, two different pieces to this reaction. Overall, what we're doing is converting reactants to products. But in this case, the second step is what's called a workup. So we'll see what I mean by that in just a second. Really what that means is after we add BH3, we form an intermediate molecule that we don't want, and then we have to hit it with the reagents in the second step to turn it into the molecule that we do want. So it's called a workup, which means we do this final conversion. Inside of here, let's talk about the different pieces. We use a specific solvent for this reaction called THF. And THF is a cyclic ether. So it's just an ether. It's in a 5-membered ring. It's used as a solvent. So if we actually say what solvent we're using, that means I don't have a lot of variability with the solvent. So there's a lot of different solvents in the world. I have to use THF for this reaction. And we're not going to go into the details of why we need to use this. But this is part of, learning organic chemistry is learning the names of specific solvents. And so this one's called THF. Well, it's actually called tetrahydrofuran. Nobody calls it that. Everybody calls it THF. But you are expected to know the structure of this solvent. I won't ask you to draw it, but if I give you this molecule and say, okay, what's the name of this, then you need to come up with THF. So this is, things that are going to crop up as we go through organic chemistry. Sometimes we need a specific solvent, and so you've got to understand what that means. So in the second step, we use H2O2, which is hydrogen peroxide. This is used in the workup. And this we'll see this later. It's just used to make the final conversion. And remember here what we're starting with is BH3. That's really the reagent in this reaction. And BH3 is sort of an interesting molecule in that it's one of the few species on the top of the p orbital row that can have a violated octet. So when we talk about oxygen, nitrogen, carbon, remember we made a big deal of saying that when they're in a positively charged, or excuse me, when they have a violated octet, they're very unstable and such that they won't stay around. They'll grab electrons from something. So with borane, though, it actually can be stable as a violated octet. So borane is BH3. It only has 6 electrons around it. It's stable enough that you can actually have borane as a reagent. We can use it. It's stable over relatively long periods of times, but it really is electrophilic. By that we mean it wants electrons. So this species, even though it's stable with 6 electrons, it still really wants 8. It wants to obey the octet rule. So if there are any electrons around, it will grab onto it to get to the octet, to get to the 8 electrons. So basically what we're saying is borane is very electrophilic, and that's what's going to start this reaction out. So when we look at the mechanism, it's a little bit different than what we've seen, and it doesn't really follow the true electrophilic addition. And we're going to talk about it in a basic sense, but I want you to understand a couple of things here. And really what we're leading into is the positioning of the bonds. So when we add the H and the OH, how are those bonds going to be positioned in my product? So in the first step of hydroboration, you get a hydride addition. So remember, a hydride is just a hydrogen with electrons. So I don't know if I talked about that, but a hydride is the hydrogen and the electrons inside of the bond. That gets added to my double bond. So here in this first step, there's 2 arrows. So the first one is the pi electrons are attacking the carbon, attacking the bromine. So we do get a type of electrophilic attack. Remember, double bonds are electron rich, so this double bond is attacking the borane here, and that's because it has a violated octet, so it'll pull electrons towards it. So a bond attacking an atom forms a bond. So this arrow, the electrons in my double bond attacking the borane forms this carbon-boron bond, and then in the other part, the electrons in between boron and hydrogen, these electrons attack the other carbon. So a bond attacking an atom forms a bond. And so this ends up breaking the boron hydrogen bond, so we lose hydrogen from boron during this reaction, and these electrons move to this carbon, so we end up forming a carbon-hydrogen bond. One piece I want you to show is that this is happening at the same time, and so the boron and the hydrogen are kind of coming in parallel to the double bond, and that's going to have an effect on our positioning later on. So after this first step, we form a type of boring compound. So remember, overall during hydroboration, you want to form an OH, so we're not quite there yet. So this is why we had step 1 and step 2 inside of our reaction. After step 1, we form this intermediate boron compound, and then we want to get rid of that. And that's where the second step comes in. We react it with hydrogen peroxide and sodium hydroxide, and then we replace the boron with OH. And we're not going to go into the details of this. But really what we wanted to see is that during this reaction, the boron and the hydrogen are added to the same side of this reaction. And so that has to do with our positioning, and we'll look at that in just a second. But for right now, what you need to remember is we're adding an H and an OH, and in this case, the OH goes anti-Markovnikov, or on the less substituted side. So same deal, we're going to be talking about a lot of reactions that involve double bonds. It's the reagents that tell me what's going on. When I see my boron here, I say I'm doing a hydroboration. That means I break the double bond, I form 2 single bonds. What goes on those single bonds? An H and an OH, and the OH goes on the less substituted carbon. So between these two, more substituted, less substituted, so my hydrogen is going on the less substituted carbon. So this carbon here is this carbon there. So I break the double bond, forms 2 single bonds. What goes on there? An H and an OH, H and an OH, and the OH goes on the less substituted carbon. So one other piece you have to remember, and so you need to put this all together when you're learning these reactions. Do we apply Markovnikov's rule? Is there positioning I need to consider? And so here what I was trying to show is when we come in and add the boron and the hydrogen, they add to the same side. So the H and the OH that we end up making in our product are added syn, which means on the same side. So we've already seen anti, which means on opposite sides. Now our 2 bonds are added syn, and those are the 2 variants. Syn and anti are the double bonds on opposite sides of the molecule, the product molecule, or are they on the same side? So here we can show that by using a ring that makes it very, very clear. So I have this molecule, I do a hydroboration on it, I break the double bond, I form 2 single bonds. What goes on those single bonds? An OH and an H. But now beyond that, I need to be very clear that the H and the OH are on the same side. So with a ring, remember there's a defined upper and lower side. I show that inside of my product by putting the H and the OH on the same side of the molecule. I do that by using a wedge in this case. So this means that the OH and the H are on the same side. In doing this, the 2 methyl groups that are coming off of my double bond, they both get pushed down. So it's almost like the boron comes in from the top and adds across the double bond, and in doing that, it pushes the 2 species coming off of my double bond here, my 2 methyl groups, they get pushed down. So because my H and the OH, the H and the OH are on the same side, these 2 methyl groups are going to be on the same side too. And so I show that by putting them both on the wedge form. So there's a few different ways you can show this, but it's very important when you draw out the product of a hydroboration, you got to show the H and the OH as being on the same side of the molecule. So one of the other things we end up learning during organic chemistry is we're going to keep seeing this. There's going to be different functional groups that we're going to see. So that never stops. We gave you a basic list, a fundamental list of functional groups, so like esters, carboxylic acids, ethers, and alkenes and alkanes, and things like that. But as we go along organic chemistry, we're going to be introduced to new functional groups, and that's what we're going to do in this case. So right now we're talking about reactions that we can do to a double bond. And also the other thing that we learn is new kind of reagents. And certain reagents can do certain things in the molecule. So learning reagents, what do they look like? What do they do? What are their names? That's part of organic chemistry. So epoxides are made by reacting a double bond with what's called a percarboxylic acid. So this is a specific functional group, a percarboxylic acid. So we've already talked about carboxylic acids. They're very similar to carboxylic acids, but there's a slight difference. That's what the per means. So per means that you have this oxygen-oxygen bond inside of there. So like peroxide, that's what we're talking about. So a percarboxylic acid has 2 oxygens inside of there. So if I was to get rid of this oxygen, I would have a carboxylic acid. C double bonded to O, bonded to OH. But because it's a percarboxylic acid, we have an extra oxygen inside of there. And because we have an oxygen-oxygen bond, this is called a percarboxylic acid. So this is a specific functional group. So the C double bonded to O and the other bond goes to an oxygen H. That's a percarboxylic acid. So you need to be able to identify this. So just like in the first exam, if I give you a molecule that has this functional group in there, you need to be able to identify it as a percarboxylic acid. So with this is a functional group. And now we're going to talk about 2 specific versions. So these are specific molecules that we use to do this conversion. So we're still talking about turning an alkene into an epoxide. The first one is called peracetic acid. So we might have played around with acetic acid inside of the lab thus far. Remember, it's it's vinegar in this case. So acetic acid with an extra oxygen in there is called peracetic acid. So this is the literal name of a molecule. Remember, this is a functional group. Peracetic acid has a percarboxylic acid inside of there. So the literal name of this molecule is peracetic acid, but it has a percarboxylic acid functional group inside of there. When we use peracetic acid, acetic acid, and we'll see the function of this, is used as the solvent. So once again, if we say what solvent we're using, that means that we have to use acetic acid only. So there's a lot of different solvents in the world, but we have to use acetic acid. So peracetic acid, so same thing, learning different reagents inside of this class is important. So if I give you this molecule, you got to be able to tell me it's peracetic acid. And part of this, you need to understand what the reagents do. And so whenever I see a peracetic acid, it means I'm forming an epoxide from a double bond. So there's other things they can do. Really what they do is they add oxygen to things. So there's a bunch of different reactions we can do with percarboxylic acids. In our case, we're turning an alkene into an epoxide. But when I look at them, I say, am I adding oxygen to something? So another variation of this is this kind of interesting molecule. It's called metachloroperbenzoic acid. This is a specific reagent, and nobody calls it this. Everybody calls it MCPBA. But you need to know the structure of these reagents if I was to give this to you. So I'm not going to ask you to draw it, but if I give you this, you need to be able to tell me it's MCPBA. And then you need to remember that whenever I see MCPBA, it means I'm adding oxygen to something generally. So this is another reagent that we use for the conversion of an alkene into an epoxide. So we'll see what epoxide here is just a second. And with this also, methylene chloride is used as the solvent. So methylene chloride is not the reagent. It's really just a very specific solvent. And when we mention the solvent, it means I have to use methylene chloride. I can't use any of the other solvents. So let's take a look at this for how complex it sounds. It's really not that bad. We still are starting with a double bond. So notice during this whole piece, we've always started with a double bond. It's the reagent that tells me what's going on. So if you see here, this is peracetic acid, and this lower part is my solvent, acetic acid. And so I know it's a peracetic acid because I have 3 oxygens here. Acetic acid, carboxylic acid, it's CO2H. Peracetic acid is CO3H. So this is peracetic acid, and acetic acid is being used as the solvent. So with some reactions, if I have to use a very specific solvent, they will put the solvent typically below the line, and this is not my reagent, but it says that I'm using it as a solvent. But overall, going from reactant to product is pretty straightforward. I break the double bond, I form 2 single bonds, so we're still doing that. And what happens is both of the single bonds go to the same oxygen. So here we see an epoxide. So epoxide is another functional group that we haven't seen yet. It's an ether that's in a 3-membered ring. And so you guys have probably heard of polyepoxides and things like that. We'll talk about that in 335B. But this is another new functional group. An epoxide is a three-membered ring with two carbons and an oxygen. So once again, you need to be able to identify this. If I was going to give you a molecule and said, what's the functional group inside of here, you need to be able to tell me it's an epoxide. So three-membered ring, two carbons and an oxygen. That's what we end up forming when we react a double bond with a percarboxylic acid, as we form an epoxide. So here, peracetic acid with acetic acid as the solvent, we break the double bond, we form two single bonds. What goes on those single bonds? An oxygen. So both of the single bonds that we form go on the oxygen in this case. The other one was MCPBA. So this is our metachloroperbenzoic acid. So it's just abbreviation so we understand what reagent we're using. So when I see this, I know I'm using a percarboxylic acid. It means I'm forming an epoxide. And then this is methylene chloride down here, CH2Cl2. It's just a solvent. Remember, it's not our reagent. It's just a very specific solvent. It's not really doing anything particular in this reaction. But when I see a double bond and I see a percarboxylic acid like MCPBA, I know I'm forming an epoxide. Still the same basic idea. I have a double bond. I break the double bond. I form two single bonds. What goes on those two single bonds is an oxygen. So the two single bonds that we form go to an oxygen. So, you know, try not to overthink this. It's really all I do when I go from reactants to products, especially like in this one. I say, you know, whatever else is on there just comes along from the ride. I break the double bonds, go, okay, draw a line to an oxygen, draw another line to that same oxygen. I've made the product that I want, an epoxide. So with ozonolysis, reaction of ozone, so we're going to get away from our typical reactions with double bonds for just a second. So we're not going to be following, you know, San-Anti or Kobnikov rule and things like that. But this is a very important reaction, and the idea is alkenes can be cleaved through the use of ozone. So by cleave, it means we're going to be literally breaking this carbon-carbon bond. And this is kind of an important reaction because it's there's not a lot of reactions that actually break carbon-carbon bonds. It's actually kind of hard to do. And this is important because we can actually form some of our C double bond O products in this case, or functional groups. So we haven't really talked too much about forming a ketone or an aldehyde in this case. So we use ozone, O3, and this is the same ozone that's inside of our atmosphere, but the idea is we have a machine called an ozonator that will generate ozone, and you literally, if you want to do this reaction, you put your double bond in solution and you blow ozone through it, and it does this reaction. And for right now, I'll explain more of going from reactants to products in just a second. It breaks the carbon-carbon double bond, and it just puts an oxygen in its place. And then whatever alkyl groups are coming off of that carbon stays there. So we have the possibility of forming ketones and aldehydes in this case. And we'll show you here in just a second how to actually get to this. In the first step, we just blow ozone through it. So this is like hydroboration, where it's broken up into two steps. After the addition of ozone, we form an intermediate that we don't want. And in the second step, we do a workup, which means we convert the intermediate into the product that we want. And so in this case, we use dimethyl sulfide. So that's this right here. And yeah, it smells really bad. And this is what we use to cause the intermediate that we form through the addition of ozone. This is what turns it into our actual products here. And we'll look at sort of the mechanism here in just a second. It's just kind of interesting to see how do we actually break a carbon-carbon double bond. So we'll take a quick peek at that. So in the mechanism, overall what happens is we get that kind of two-way street. So don't worry about this mechanism too much. I'm just kind of showing what's going on in here, and that we end up connecting this oxygen to this carbon and this oxygen to this carbon, and we form this kind of five-membered ring here. And in doing that, it actually switches. So, you know, once again, I'm not going to ask, you know, I'm just trying to show you what's going on here in terms of the addition and how do we break a carbon-carbon bond. So I'm not expecting you guys to know this mechanism per se, and just want to show you what's going on. So we add ozone. Remember, ozone is O3. We add the ozone across the double bond. So in a way, it kind of has the additions that we know, that we break this double bond, we form two single bonds. These two single bonds are going to my ozone. So we form this very strange five-membered ring, it's unstable, and what happens is it rearranges and puts one of these oxygens between my two carbons. So in 2 steps here, the first step we got rid of the pi bond, and then there's still a sigma bond remaining, or the single bond. And in the next step, by inserting an oxygen inside of there, we have gotten rid of the sigma bond. So we've completely separated these 2 carbons. We form this intermediate here, and then we react it with dimethyl sulfide, and that's what turns our intermediate into our products here with the carbonyl. With this, I can't stress this enough, and I'll give you guys some more examples of this. Do not overthink this reaction. So I know there's a lot of weird looking things going on, but in reality, going from reactants to products, which is really what I want you to know, it is not that hard. So when I am given this problem, remember, a lot of reactions with a double bond, it's the reagent that tells me what's going on. When I see O3, it tells me I am doing an ozonolysis, which means I'm going to be cleaving this double bond. So there's going to be 2 products here, one from the left side of the double bond, one from the right side of the double bond. Literally what I do is I draw a line down the middle, and you can see these 2 carbons are already set up to have a double bond inside of them. The 2 bonds on the left-hand side go to an oxygen, and the 2 bonds on the right side go to an oxygen. So I draw a line down, and I just draw a double bonded oxygen here, double bonded oxygen here, and I've got the products. So let's look at what that looks like. So I break the bond, so I just draw a line down there, and instead of these 2 lines going to a carbon, I have the 2 lines going to an oxygen. I just literally draw 2 lines, oxygen here, 2 lines, oxygen there. And that gives me the product of the reactions, and that's really what I want from you guys. So when I look here, this carbon is this carbon inside of my products. So we still have a CH3 and a CH3 coming off of it. That's true, CH3, CH3. But now the 2 lines from this carbon, so this carbon right here is this carbon right here, those 2 lines, instead of going to the other carbon, those 2 lines are now going to an oxygen. It's that easy. Same thing on the other side. What's coming off of this carbon is an H and then an ethyl group. And we still have the same thing, H and an ethyl group. So this carbon is this carbon right here. We have an H and an ethyl group coming off of it. Same thing, these 2 lines, instead of going to another carbon, these 2 lines are now going to an oxygen. So in doing this, depending on what alkyl groups you have coming off the double bond, I can either form a ketone or I can form an aldehyde in this case. So I don't really think about it too much. I just know, we break this bond, the 2 lines are going to go to 2 oxygens. I have my product. So probably one of the more important reactions we talk about in terms of reactions with alkenes is called hydrogenation. So this is another named reaction. It's a specific name, and really it does exactly what it says. So hydrogenation means we're adding hydrogen to our double bond. And in this case, we're getting rid of the alkene functional group. We're forming an alkane. And we'll talk about that later, like why do I want to get rid of a functional group and convert it to an alkane. So remember, an alkane really is considered as not having a functional group. So we'll talk about that in 335B. Why do I want to get rid of a functional group? But this overall reaction, hydrogenation, we're still going to be doing addition to a double bond. And in this case, what we're adding is hydrogen. So when we say hydrogen, we're talking about hydrogen gas. So I've seen this reaction done a bunch of times. They really bring in a canister of hydrogen and they blow hydrogen through whatever solution that we're interested in. But the hydrogen needs some help. So we need a transition metal catalyst. And there's one of 3 that you can use for this reaction. I can either use nickel, palladium, or platinum. And I need this metal catalyst in order for this reaction to occur. So just blowing hydrogen through a solution that contains a double bond is not going to be enough. I need to have some of this catalyst inside of there. And remember, with a catalyst, it means that I only need a very small amount. So one of the things I want you guys to remember, and this comes from the reaction itself, is that the hydrogens are added syn to my double bond. So because we're adding 2 hydrogens, there's no Markovnikov or anti-Markovnikov. But remember, one of the things that we want to remember is there a positioning situation with what we're dealing with. Overall, with this one, it's just like what we've been doing. I have an alkene, I break the double bond, I form 2 single bonds. What goes on those 2 single bonds? A hydrogen on each one. So there really is no Markovnikov's rule involved because we're adding a hydrogen to both sides. But I break the double bond, form 2 single bonds. I've added 2 hydrogens. And then now we need to remember that the hydrogens are added syn. And this has to do with the use of the transition metal catalyst. So that's something else you want to remember. The 2 hydrogens that we have added are going to be on the same side. And then also notice we've converted our alkene into an alkane. We've gotten rid of the double bond. So if we look at an actual example, it's, try not to overthink it. Remember, we have hydrogen up there. We'll put H2 that tells me what reaction's going on. This catalyst can change. So here I have nickel, but I could have used palladium or platinum. Here I give a specific example. I break the double bond. I form 2 single bonds. What goes on those single bonds? Hydrogens. And then I need to be very clear to show that they are on the same side of the molecule. So here, this carbon is that carbon. It went from a methyl group and a hydrogen to a methyl group and 2 hydrogens because I've added hydrogen to it. Same thing on this side. This carbon had 2 hydrogens. Now it has 3. And so the same thing when the easiest way to see syn and anti-positioning is to use a ring. So if I give you a reaction on the final exam, if it involves a ring, you need to pay very close attention to your products because I'm probably testing you to see if you understand the positioning of the reaction. So here, starting with a double bond, that doesn't tell me that much. I look at the reagent. The reagent I see is H2, in this case palladium. That tells me I'm doing a hydrogenation. A hydrogenation means I'm breaking the double bond, I'm forming 2 single bonds, and a hydrogen is going to those 2 single bonds. But during a hydrogenation, I need to be very clear to show that the hydrogens are adding syn. So in a ring, there's a defined upper and lower bond. I need to show that these 2 bonds for the hydrogens, so I broke the double bond, formed 2 single bonds. Those 2 single bonds are going to hydrogen, but I need to be very clear that the hydrogens are on the same side. So I show this by using the block formation. So this hydrogen and this hydrogen are on the same side of the ring. Same deal, I had 2 methyl groups coming off of it. Those methyl groups are pushed down. So because the 2 hydrogens are on the same side, the 2 methyl groups are on the same side. And then the methyl groups are going down or on the same side of the molecule, and I show that by using the wedged form.